Okay, this is Dr. Long-Qing Chen. He is a professor of material science and engineering, and he is going to be hosting the PAC Fellowship seminar today.
Okay,
Go ahead.
Thank you. Thank you for coming to the meeting. I'm also have a courtesy appointment with mathematics and also engineering, science, and mechanics. And I'm located in the Millennium Science Complex. It's a new building which hosts the Material Research Institute. And what I would like to talk about is really a recent work showing how we can use computer to guide the discovery of, in this case, a transparent piezoelectric crystal, but with very high piezoelectricity. And we're actually talking about an existing crystal, but I don't know if you can see my cursor. When I move my cursor, can you?
Yes. Yeah, I can see it. Yes.
So typically a piezoelectric crystal with very high piezoelectricity look like this. It's opaque. But during the past year, we were able to, actually been like 2 years, we're able to make it transparent like this. And the whole thing was really a combination, of course, experiment and computation, but I like to talk about how our computation was able to help our experimental collaborators to achieve the transparency and at the same time also very high piezoelectricity. And this was published recently in Nature, just a month or 2 months ago. So let me give a very brief introduction to what is piezoelectric effect. I assume most of you know this pretty well about piezoelectric effects, but in case there are students who turn in and not familiar with this. So piezoelectric really means if you apply a mechanical force or mechanical stress, the material will generate an electrical signal. So here what I'm showing is let's say that we apply a mechanical stress, then the crystal will produce electrical displacement. And in general, in crystals, we represent these quantities using so-called tensors or vectors. And stress is a second-rank tensor, so electrical displacement is a vector. And the property which connect these two, representing this effect, when you apply stress, how much electrical displacement exhibit of a crystal is represented by this piezoelectric coefficients, because it connects a second-rank tensor and a first rank or a vector, or a vector, it's a third rank piezoelectric tensor. And this is called the direct effect. We're talking about piezo means apply mechanical stress, produce electrical displacement. So it's a direct effect. And essentially, if you apply a stress, you can generate an electrical signal because of the charge produced on the surface. There's also a corresponding converse effect. So in this case, if we apply an electrical signal or electrical force, it's electrical field or electrical potential difference, then we can produce a mechanical deformation of the crystal. Again, this effect is represented by this third rank tensor D, the converse piezoelectric coefficients. And it can be showing actually this coefficients representing the direct effects and the converse effect, they are equal. And you can imagine, because of the ability of a crystal which can convert electrical energy or electrical signal to mechanical energy or mechanical signal or vice versa, they can imagine many different applications. For example, for direct effect, we can talk about sensors. So you can sense a mechanical force or vibration or a sound wave by detecting electrical signals, or we can produce motions, we call actuators. When we apply electrical signal, you can produce mechanical motion. So some of the examples, they're actually a lot more listed here, like ultrasonic transducers or vibration sensors, underwater sonar systems, and some of the common devices we're all familiar with, like even fuel injectors and grill igniters or speakers. Now, there have been quite a few milestones. Roughly the early days of discovery, that's more than 100 years ago, like in quartz. Then in the 1940s, a discovery of a ferroelectric barium titanate, which has a much better piezoelectric effect than materials that discovered in early days like a quartz. And then the 1950s, now the discovery of PZT, which is really a solid solution of lead zirconate and lead titanate, and it has a so-called morphotropic phase boundary. And around the morphotropic phase boundaries, there's a phase coexistence of rhombohedral and tetragonal phases. So actually also now has a much higher piezoelectric response than single crystals like a barium titanate or barium titanate ceramics. And then the next milestone is the relaxer, ferroelectric ceramics. And then about 20 years ago, that was discovered at Penn State. Oh, somehow automatically replaying. Okay, the discovery of single crystal here at Penn State in relaxer lead titan or relaxer ferroelectric crystals. So we're talking about roughly a 1,000, maybe order of magnitude. So it's a 1,000 times larger now compared to the very initial piezoelectric materials. And these materials exhibit much higher strain under electrical field, and also exhibit very high coupling, which means the electromechanical coupling coefficients. So what's next? You know, what can we do? It's been like 20 years. There was really not a whole lot of progress in terms of achieving higher piezoelectric piezoelectricity or materials with much higher piezoelectric responses. And also the questions that whether or not can computation help to achieve the next milestone or the future milestones. So in our my own group here at Penn State, we have been using so-called the phase field method. So this is a computational method that we have been involved and developing models for different applications for quite maybe 20 now, almost 30 years. So this is a continuum method. So we describe a microstructure. Actually, in this case, any microstructures using a continuum description. So you can think of in terms of thermodynamics, each point in a microstructure is a thermodynamic system. And you can think of each point now has its own fundamental equation of thermodynamics, which means describing the local chemical potential or free energy density as a function of the local properties. So here I'm trying to show a schematic representation. Let's say we have a microstructure, which I am listing quite a few number of quantities. You can think of like a C, the compositional, chemical compositional distributions, P, maybe like a polarization distribution, or you can also have magnetization distribution, or mechanical strain distributions. Or you can even include things like cracks, crack opening in different locations, or even dislocations represented by dislocation, Brooks vector distributions, as well as possibilities of ordering, atomic ordering, or phase separations, or anti-phase boundaries, or grain boundaries. So depending on a particular problem, you can find a set of we call fields to represent a microstructure. Of course, for particular material, we don't need all these fields, but just here, just saying that you can represent any arbitrary microstructures. So each point, as I mentioned, the local free energy density is can be a function of local thermodynamic or local parameters like temperature, the chemical composition, these fields, values, strain, polarization, magnetization. And then we're looking at the thermodynamics for inhomogeneous systems. So you add up the contributions from, this is represented by the first term, the contribution from the local energies. Well, integration really means adding them up. But also you have interactions. Let's say if you have different regions with different compositions, you have interfaces. So you have changes in those fields, whether they are composition or strain or polarization. These big changes represent interfaces. So we also have interfacial energy contributions. And also in a crystal or in a ceramics, when you have heterogeneous microstructure, very often you have long-range elastic interactions because different regions of the material, they have different stress-free lattice parameters. In order to accommodate each other, they will have long-range elastic interactions. We can have inhomogeneous charge distributions. So you have a long-range electrostatic interactions, or if we have a magnetic materials, then you have magnetostatic contributions, and some of these elastic, electrostatic, and magnetic interactions are long-range interactions, so they are not local. We have to obtain those by solving also the corresponding equations, the elasticity equations, and for example, the electrostatic equilibrium equation, then also the magnetostatic equilibrium equations. So the whole idea here is now we have so many, we can have more than one fields to represent a microstructure, but you don't really have to evolve all the all the fields in a microstructural evolution. Some of them, they evolve faster than others. For example, long-range diffusion in a microstructure in materials usually evolve a lot slower than other processes like mechanical displacements. They will evolve to equilibrium a lot faster than long-range diffusion. So typically, we're assuming those fast evolving fields are like a steady state or quasi-steady state equilibrium conditions or equilibrium states, and only evolve in the low, slowly evolving fields, like a diffusion equation in evolving a microstructure. One of the main advantages, you automatically couple different contributions to the thermodynamics of microstructures. You know, this can be chemical, can be thermal, electrical, mechanical, magnetic, for example. So that you can incorporate all these different contributions in the same model. I'm showing one slide because this whole phase field method it depends, utilize this, we call the diffuse interface description. So the interface is between different phases or different grains are not mathematically sharp. They exhibit gradual changes for the fields. But this is, I can claim actually even similar to the well-known density functional theory in solid state physics. And actually a lot of materials people also now using this density functional theory to do calculations, electronic structure calculations. Here I'm showing, in density functional theory, you can think of the crystal has an inhomogeneous electron density distributions, but then the total energy is a functional of this electron density. So you have terms of the electrons in the presence of an electrical potential field. So you have this electrical energy, but also there's the Coulombic interactions at the second term, the long range interaction. That's why involve a double integral. And then there's a local energy, which is G0, which essentially only depends on local electron density. Then we have this, similar to exchange terms in magnetic, describing magnetic materials. And this is in density functional theories, also called kinetic energy and exchange correlation terms. But now if I have electrical dipole density pattern or ferroelectric domain structure, now in the phase field description, the interfaces are diffuse. So just like in electron density distribution, they actually is a continuous function in space. There's really no sharp interface from one atom to another, for the electron density. So here from one domain to another, the polarization is continuous. So mathematically, they are almost equivalent. Now here we're talking about free energy, which is a functional of the polarization distribution in a domain structure. We have a first term, if we have a local electrical field, so you have this, this electrical field can be generated inside due to the presence of charges, or can be applied electrical field. So you have this interaction term. Well, I guess this is, we'll separate. This is mostly from the external, the first term. And the second term represent more like a dipole-dipole interaction that's inside the crystal. And then we have a local term, which only depends on the local polarization. We have exchange term. So now this local term, we call the bulk free energy contribution, and we have gradient energy contribution. So there's almost one-to-one correspondence. So even when we're talking about phase field method, a lot of people are more familiar with density functional theory. I say mathematically, if we're just looking at the equilibrium, they're actually very similar. One is trying to minimize the total energy with respect to the electron density distribution, but in the phase field method, we try to evolve the microstructure to lower the free energy of the whole microstructure by evolving the fields which represent the microstructures. Now, through the years, we have built our own software package. We even commercialized actually part of it. So we have this so-called MIL-Pro simulation package. Essentially, it's a phase field package. It's quite convenient to use. We have tools for both input and for output processing. For example, input, we have own small thermodynamic databases for different crystals. And then also we have tools to generate initial microstructures, or we can import microstructures from a previous simulation or import microstructures generated from experiments as input. And we can set up also, we have ways to set up high throughput calculations. For example, if you want to generate a diagram, let's say how the domain structures of a ferroelectric crystal will change with temperature and strain. So we can fire up hundreds of simulations, just like experiments. In order to generate a phase diagram, you will need to look at different compositions, different temperatures, and try to determine what are the equilibrium phases. So here we're almost doing the same on a computer, but we can do it in a high throughput way on the computer. And the code is native to Linux systems, but we can run this using a Mac or PC also. And so far we have modules for doing ferroelectric domain modeling, magnetic. So this magnetic module is very similar to a lot of those micromagnetic codes out there. The main difference will be we also couple with the mechanical strain or mechanical strain energy contributions, but also can be coupled with the ferroelectrics. And also we have a module which can do effective property contribution. So far, most of them for linear properties, such as effective modulus, effective dielectric constants, effective piezoelectric coefficients, or effective kinetic properties like diffusion coefficient, thermal conductivity. But if we want to do the nonlinear response, we directly use the ferroelectric or the magnetic codes to do, for example, switching. And also now we have these output tools can generate images for different stages of evolution, or it can produce animation directly from the simulation. And also we have ways to back up the output, the images from simulation, because now there's a lot of talk about big data, data science, machine learning. So this is one way actually to generate data, because in order to do learning, we need data. And using the simulation tool, we can generate tons of data, and either we can use to validate certain machine learning method, or can be also used as a part of the data to do learning. But so far, most of the computations, this is actually true, maybe the whole computational material science and computational physics fields. Most of us being focused on understanding. This can include, of course, we're developing the most of the time still trying to developing models or ways to compute different material systems or processes, and try to reproduce experiments or understand what was observed experimentally. And sometimes we use the computation to test analytical theories, or even just try to illustrate, hey, how a particular process taking place, or how the microstructures evolve. So far, most of the efforts have been focused on this type of problems. So I've been trying to encourage really the people in the field how we can move from such a efforts focused on understanding to prediction and discovery of new phenomena. In our case, new phenomena and new mesoscale microstructures, how we can actually use computation to guide experimental synthesis, or in the case of people doing things in growth or crystal growth, or whether we can use computation actually to do optimization of the property of a property of a material, or maybe a combination of properties. Sometimes we want to optimize a combination of properties. That's actually pretty often. For structural materials, we like high strength but also we like to have high toughness. Or for the dielectric materials, we like to have high breakdown strength, but also we want to have low loss. And a lot of times, actually, these different things are for thermoelectric materials. You want to lower the thermal conductivity, maybe increase the electrical conductivity, and many of these actually go opposite ways, or actually go the same way or opposite ways in general in materials. So how we can use computation to help to do this type of optimizations. In our case, we will be with respect to microstructures. Now, in terms of understanding or reproducing experiment, we actually have many examples. We have shown that the simulations, if you incorporate the right physics, you can predict the microstructures in very good agreement with experiments. So here, just a couple of experimental images for bismuth ferrite crystal. Actually, these are from thin films showing the different colors actually represent different domain structures in bismuth ferrite. Oops. You see what I show in this from our phase view simulations. As you can see, we can reproduce or predict these domain structures very nicely in excellent agreement with experiment. And of course, one thing we can do a lot more in the simulation, we can dig into, hey, what are the local stress distributions or local polarization distributions, and still can learn a lot, but still here we are more, say, trying to explain experimental observations or even more complicated pattern. This is a kind of actually high resolution TEM pattern for a superlattice. I'm not going to go to the details here, just say we can also reproduce very complicated polarization patterns and understand why they form. But these are still, it's not like hey, we try to do the simulations and tell the experiments, say, hey, maybe you want to go and find this, or you try to change your processing conditions to discover new phenomena. Now, this is a couple of examples that we were able to achieve in the last few years in terms of prediction. And this is one of the examples that I think we achieved maybe 3 years ago for superlattices. We were able to predict, I'll briefly mention later on also in the talk, actually was our prediction and then experimentally validated so-called the formation of vortex lattice. And also I briefly mentioned that through the phase view simulations, then our experimental collaborator was able to choose the right dopant to dramatically increase the piezoelectric effect of ceramics, and also showing that you can actually try to find what is the optimum. In this case, this figure I've just showing is what will be the optimum breakdown strength of a composite ceramics particles, or actually it's a polymer filled with ceramic particles, or the ceramic polymer composite. What is the optimum shape of the ceramic particles? What is the optimum volume fraction? So I'll just quickly show two examples. One is discovery of this ferroelectric polar vortex lattices and skyrmions in a heterostructure, or in this case, a lead titanate, strontium titanate superlattice. In this case, we say guided by phase view simulations, but actually we literally predicted first under what kind of periodicity of the superlattice, under what substrate you can achieve such a periodic vortex, which means the polarization actually are rotating rather than along specific directions, as most of the people believe in the conventional ferroelectric crystals. all the polarizations are pretty much set along a certain crystallographic directions. But here we are actually forming lattice. We can actually compute a phase, like a phase diagram. Say if you change periodicity along the horizontal axis, if you change temperature. In this case, we're just plotting, say, under the different thickness, what will be the stable polarization configurations? So they change a lot from we so-called the in-plane twin domains to vortex lattices, and then normal ferroelectric domains as you change the thickness of the ferroelectric layers. And also if you try to change temperature, or if you try to apply a field, you can manipulate all these polarization distributions. Not only you can have the different domain states, but they can have coexisting states. You can have a coexisting twin states and vortex states, just like these different polar states, almost like a different phases in a normal phase diagram, and they can coexist. If you change the substrate, you can also totally change the polarization distributions. Here we show that they form like can be skyrmions, which means the polarization actually has been turning these bubbles. It's not the polarization just up and down, but also they are turning. Now you can also, in the simulations, we can compute the local properties. And one of the things we discover also locally in such a polar lattice or polar vortex lattice and skyrmions, there are regions of negative electrocapacitance. So that's really related to the second derivative of energy with respect to in this case, polarization. And also if you hit it, a states like the mixed twin and vortex states, you can produce even fascinating, we call supercrystals. So in this type of, in this series of work, the simulation is actually leading the effort. Or basically tell the experiment, say, hey, go find this type of polarization states that we find in the simulation. And almost so far, every single case, they were experimentally able to validate our predictions. Now, this is another example, also about 3 years ago when Dr. Fei Li was here as a postdoc and research associate for 3 years. By doing simulation, how we putting a little bit rare earth in a PMN-PT crystal, how that can change the dielectric responses. First, we try to discover what happened, what really these dopants do, this heterogeneous dopants in the crystal, and we relate to the dopants, the amount of dopants, and also the amount of dielectric loss. Trying to pick, now though this loss in the first figure is showing the low temperature, so very low temperature, only those small nanoscale polar regions are responding. And somehow if we have more of those nanoscale regions, we can achieve high piezoelectric response. So experimentally, we try to pick a dopant which also give us a much higher low temperature response, which means these contributions from this heterogeneity, which actually can promote the polarization rotation under electrical field, which enhance the piezoelectric crystal. So indeed, using Smirlian doping, we were able to dramatically increase the piezoelectric response of a PMN-PT ceramics with just a little bit doping, and was tested in a needle-shaped transducers with much actually better performance. And later also using this Smirlian doped PMN-PT chemistry also was used to grow thin gold crystals, and now was able to double, almost double. It's a 90% increase over the piezoelectric response, which was achieved about 20 years ago here at Penn State. So if I show this milestone, because due to the guidance of our simulation, we discovered this Samarian doped PMN-PT crystal, almost double the piezoelectric response from the crystals from about 20 years ago. So we were actually pretty happy in this case that simulations were able to provide the guidance. Now, actually the main story I like to tell today in this talk is about the piezoelectricity enhancement due to AC polling, alternative current electrical field polling. So rather than DC polling, which means you apply electric steady electrical field for a certain amount of time and you remove it. But here it's just going the electrical field going back and forth. So this was discovered by, excuse me, John Yamashita about 8-9 years ago. He showed that just by AC polling rather than DC, he claimed he can increase the piezoelectricity of, in this case, a ternary relaxer ferroelectric crystal, almost doubled. You know, as you can see in his picture, it's almost achieving almost like 4,000 picocoulomb per Newton, and this is almost double what was achieved in the crystal. People typically use DC polling. So this was not too many people actually pay attention to this discovery until the last few years. Now there were quite a bit of activities to try to reproduce whether this is true. And here just showing you a couple of examples. One is by Xiaoying Zhang from NC State here in the United States. Was trying to reproduce also the enhancement of a piezoelectricity due to AC polling. So indeed, if you see the first figure, of course, if it's unpoled, then it's like there's no piezoelectricity, even though it's a ferroelectric crystal, because the random orientation or the average polarization is 0 if you don't pole. A DC pole is about 1600, but now if you go through this AC cycles, it's like it's gradually increase and eventually saturate. So through the AC polling, you have now about 30% increase in the piezoelectric response. And that's, even though this is not double the values claimed by John Yamashita, but this is very significant in the sense that this AC polling is not complicated. It's very easy to do. It's a low frequency. It's like 1 hertz, you know, it's just going back and forth a few more times. Also here at Penn State, when Fei Li was here, we went through many different compositions and compared AC polling and DC polling. Indeed, if you look at the last column, the values of the piezoelectric response compared to the DC polling, the last row, indeed, we're getting also about 25–30% enhancement. So this is, it's true, actually, AC polling can help enhance the piezoelectric response of a crystal. And now, why this happens? Most of the existing works, actually all of the existing works, indicate the reason that AC polling can significantly increase or enhance the piezoelectricity is because of, say, the domains become smaller. So the AC polling is almost like a domain refining process, because most people believe the domain wall contributions to piezoelectricity can dramatically enhance the piezoelectricity of a crystal overall. Okay, so the reported explanations of why the AC polling can enhance piezoelectricity is almost entirely attributed to the refining of the domains. This idea of refining domains to enhance piezoelectricity also came from the earlier work by Wada in Japan. In the work, he worked on barium titanate, ceramics. He claimed that the piezoelectricity will enhance. Actually, he showed enhancement in piezoelectricity when the domain is actually getting smaller in barium titanate. And now he also even extrapolate based on his experiment, you can get a huge, humongous increase in piezoelectricity by refining the domains. Now, I'm not going to go to the details of why it's so in barium titanate, because barium titanate is actually a tetragonal ferroelectric crystal. Now for PMN-PT, it's actually it can be tetragonal, but mostly it's a rhombohedral or a mixture of a rhombohedral tetragonal crystals. But anyway, all the existing works claim it's because of smaller domains. And actually I can show you many, many more examples right here. It just a higher domain wall density is responsible for the enhanced piezoelectricity over DC pole crystals. So all the AC polling going back and forth electrical field, all it does is increase the domain wall density or make the domains smaller. So what we do is say, hey, what happens if we just put on a computer? The computer tells us, say, whether or not if we do AC polling, whether the domains actually will become smaller or larger. So here, we just put into, so here the two movies showing on the left-hand side is a DC polling. So below showing how the electrical field we apply, in this case, you just apply a steady state electrical field. So you see a layer structure with different colors representing domains with different polarization directions in a rhombohedral crystal. So we choose the composition of the crystal in such a way the ferroelectric state is a rhombohedral crystal. Now, if we, on the right-hand side, this animation is showing as we go through this alternative electrical field going back and forth, you keep going through nucleation growth, back and forth. But as you can see, the overall at the end of the AC polling, the domain size actually is getting bigger rather than smaller as claimed by all existing efforts or in the existing literature. And this is true whether we do it in 2D or doing in 3D. So if you compare the initial domain structure, it's much smaller. If we do a DC polling, also poll into a layer structure, but still with a lot of domain walls. Now with AC polling, there are either no domain, only very small, well, because here is we still have a set of domain wall. We use the periodic boundary conditions and we constrain the crystal. But now if we let the crystal stress free, all the domain walls, the slanted domain walls actually disappear. All left are these layer structures with the domain wall perpendicular to the polling direction. And this domain walls, we call this a 109 degree domain walls, which means the polarization actually changed direction by 109 degrees. All these tilted domain walls are 71 degree domain walls. And this is corresponding 3D. And during the simulation, we can also show that the different energetic contributions that most of them actually decreasing. So it's indeed is supposedly the way that should happen based on thermodynamics. The domains actually should be getting bigger. So this is totally different from the existing experimental observation. Now, we have to also now do much more careful experiments. Now, most of the existing experimental efforts, the observations, are rely on PFM, or the piezo force response microscope. I was told by those experts in PFM, say those are really only surface sensitive methods, which means only probing the polarization domain structures near the surface, like 10 nanometers. But these are pretty a good size of crystals. And also on the surface, because of polishing, because of defects, you see from the surface, not necessarily reflect the domain structure inside the crystal. Now here, Fei Li, well, our collaborator, as I mentioned before, he was here at Penn State for 3 years. So he was really the one actually also driving this, research, trying to see how AC can influence the piezoelectricity. Now, through careful polarized light microscope, we see indeed the changes that we saw from the simulations. As you go see from the first figure is a DC poled sample. And then let's go through cycle 1 of the AC polling, cycle 2, go to cycle 10. If you look from the top of the crystal, all these patterns you can think of, these are actually 71-degree domain walls. They are these cross patterns. After cycle 10, just 10 cycles, you don't see those domain walls anymore, which means the domain is actually getting bigger, not getting smaller as was claimed by all the other efforts reported in the literature. Also, we try different frequencies of polling. Here, almost shown the same result. So it's pretty robust. You can use 0.1 hertz frequency to 100 hertz frequency. They all at the end, we're getting almost look like a single domain from the top, right? So, and the bottom is actually showing the DC poled, now still much actually finer domain structures. Now, because of this type of domain, so we were thinking, oh, wait a minute, if indeed the domains are so big, then the crystals actually could be transparent. So we look at the birefringence imaging microscopy also. So in this case, as I mentioned on these images showing this, domain walls, horizontal domain walls, we call 109-degree domain walls. And this tilted is a 71-degree domain walls. So if we look at the optical indicatrix, so across the 109-degree domain wall, this indicatrix or this ellipsoidal actually doesn't change. But across the 71-degree domain wall, they actually rotate it. So which means the 71-degree domain wall will reflect light, but the 109-degree domain wall is actually the light will go through, actually, or will transmit. So this is the images from the birefringence imaging microscope, or called BIM. This is unpoled, showing right here. So it's pretty messy domain pattern. This is DC poled, quite fine domain structures. Now AC poled, just after 3 cycles, you really see very few of this domain walls, 71-degree domain walls. And if you go to 10 cycles, again, just like in the polarized optical microscope, almost you don't see the 71-degree domain walls. This is just showing if you now do a cross section, which means vertical or parallel to the polling direction, still seeing the layer structures, both AC pole, DC pole. So along that direction, still the thickness is almost the same. So only now within each layer in the AC pole samples, it's almost like a single domain. Okay, so here I'm just trying to do a comparison of what we predicted from phase field simulations and also then the experimentally observed domain structures of AC pole and DC pole PMN-PT crystals. So on the right-hand side, there's a DC pole with a lot of more domains, smaller domain size. The left-hand side is an AC pole using both 2D and 3D simulations. Now, this is SEM images. Actually, it's much clearer comparison. The AC pole on the left is just layer structure, almost like a single domain each layer. But DC pole, you see a lot more domain walls. And if you look at the X-ray diffraction pattern, this AC pole, you'll see that 222 reflection spot is much sharper compared to DC pole or unpoled. Right? And now, after we actually submitted our Nature article last year, a few months later, this the same Yamashita group who discovered this AC polling, although previously they claimed the smaller domains, now they also show similar layer structures, just like we predicted from the simulations. And now we also trying to determine, hey, whether or not if the domains are getting bigger for PMN-PT crystals, but it's supposedly what happened to the piezoelectricity, because most people think that the domains, the smaller, should give you bigger piezoelectricity. So we try to analyze for this case for the rhombohedral crystal. It's actually indeed, if we have actually smaller domains, so if we have this 71 degree domain wall, which means there's no 71 degree domain wall, so we call essentially these are infinite, so single domain. And this domain's 259 degree, is 259 nanometer size. So we're reducing the domain size of these 71 degree domains, so within each layer, right? And if we now try to compute with the dielectric constant and the piezoelectric constant, indeed, actually the bigger domain, so no domain walls has a highest piezoelectric response. So although we theoretically show actually big domains give you higher piezoelectric response rather than smaller domains. Now we did the same calculations for barium titanate. Barium titanate is different when you have a tetragonal crystal along with the polarization along those cubical axis. If you pull along 111 direction, indeed our simulation, where our calculations actually show the smaller, the better. But this is actually quite different. So this is not a general conclusion, say smaller domains favor the piezoelectricity or bigger domains favors piezoelectricity. It really depends on the polarization direction, the crystal structure, and the polling direction. Here are the properties actually were listed here, comparing the DC pole and AC pole crystals from the dielectric constant to phase transition temperatures, and also some of these optical properties measured. Now, I just want to point out in particular the piezoelectric response in terms of picocoulomb per Newton. The DC pole is around 1700 or 1670 plus minus 30 compared to about 2200 for AC pole. So it's about 30% enhancement. And both of the AC and DC pole now electromechanical coupling factors are all very high. And also in terms of optical properties, now we have a much better, higher biorefringence in the AC pole crystals. we didn't really measure this electro-optical coefficient for the DC pole because there's a lot of domains, and it's still really opaque. It's not really transparent. So what happened is, as I mentioned, the way that behave in terms of the 71-degree domain walls and 109-degree domain walls, it turns out now those AC pole crystals not only has higher piezoelectricity, about 30, even more than 30% higher, but also now the light actually can go right through, because this is horizontal walls will let the light go through, but the 71-degree domain walls will reflect. So the DC pole crystals still have a lot of these 71-degree domain walls, and they appear opaque, but there's the crystal pole using AC. Now with those essentially only 109-degree domain walls, it's like a transparent. And if you look at the right-hand side figure in terms of the transmittance of light, for the visible light region, wavelength region, as you can see, compare the AC pole crystals compared to DC pole, there's a big difference. Okay? And so this is a comparison by refringence, as well as piezoelectricity, comparing AC pole and AC pole and a DC pole. And this is a piezoelectricity of a DC pole and AC pole. So there's a huge enhancement in terms of by refringence, but also there's a significant improvement or enhancement in piezoelectric response. As a result, as I show on the first slide, now this AC DC pole crystal still opaque for the thick one, and the thinner one still is not very transparent. Of course, a single crystal, if you make it really thin, then some light actually will go through. But if you look at AC pole, both the thin and thicker crystals, you can see the lights right through. And this was published again about 2 months ago. Now, what are the potential applications? What is the use of this transparent piezoelectric crystal? So we're talking to a young professor here at Penn State in biomedical engineering, Raji. He is actually working on this so-called photoacoustic microscopy, and using transparent piezoelectric crystals. So right now he's using lithium niobate based transparent crystals, and try to do imaging. Now he's really excited actually by our work, because if you compare the properties of the AC pole PMN-PT, our transparent piezoelectric crystal, the piezoelectric coefficients, if you compare the second and third column, compared to lithium niobate, this is like 50 times higher piezoelectric response. If you compare PMN-PT to lithium niobate, if you compare the electromechanical coupling factor, this is almost double. So 94% compared to 47%. And now this electro-optical coefficient, again, this is another like a 7 times better, right? So this is something we are quite excited, because this crystal not only has a very high transparency, piezoelectric response, but also is highly transparent. Now we can envision not only in this photoacoustic imaging application, but also you can think of actuators which are transparent, so you can make a robotic device even invisible, if it's transparent. Or if we can make it like a screen, because of piezoelectric, if you can push it, you can generate electrical energy. So in principle, you can use like a screen, like a touch screen. Of course, using single crystal to do this is expensive, but we are thinking about maybe also do a composite lineup the crystals and you do AC polling, you may be able to make it transparent also. So I'd like to summarize this story really more like the second part of the talk, although the first half is more like an introduction. So we show that the enhancement of this 001 pole rhombohedral PMN-PT crystals using AC polling, we show it's due to the elimination of 71-degree domain walls. Okay, so it's and with a larger domain size, and this is totally actually in contradiction to the claims in the literature. So we basically claim that the increase in domain wall density is responsible for the piezoelectric response or enhancement as claimed in the literature is actually not correct. Also, we show that the polling, now in this case, AC polling, not only just enhance the piezoelectricity, but actually leads to nearly perfect light transparency of the crystal. So we actually achieve both, now enhanced piezoelectricity and nearly perfect light transparency. Okay. So we, as I mentioned, we can imagine a lot of different applications for these transparent piezoelectric crystals with very high piezoelectricity. In particular, those hybrid device applications involving medical imaging, like the photoacoustic imaging that I mentioned. Essentially, you could think about self-energy or energy harvesting, by just pushing, touching, screening, or screens, or you can think of make robotic devices invisible. Well, I'd like to acknowledge that the simulations were done by grad students, but one here at Penn State. Also, we had a lot of discussions with Tom Schraub. He was the one who discovered the high piezoelectricity in a single crystal PMN-PT from 20 years ago. He just retired from Penn State. Then Fei Li, he was at Penn State for 3 years. Now he went back to Xi'an Jiao Tong University as a professor. And also Professor Sujin Zhang from University of Wollongong, but he actually spent more than 10 years at Penn State, just moved to University of Wollongong. And also we have a couple of other collaborators who help to do some of the measurements in terms of the light transmittance and also X-ray measurement. And also I'd like to acknowledge some of the funding sources as well as computing resources, both at Penn State and the computing center supported by NSF, including the Pittsburgh Supercomputing Center. Okay, I think that will be the end of my talk. I'll be happy to discuss if you have any questions.
Thank you very much, Long-Qing. It was a very impressive talk. Thank you.
Oh, thank you.
Yeah, so I actually have a couple of questions. So may I start?
Yeah, go ahead.
So in your computation, so how large are your volumes? Do you use single atoms, or is it finite size volume for this phase field modeling?
For this phase field model, we can actually add different spatial scales, really depending on the problem.
Yes. No, I meant with this transparent piezoelectric crystals.
Yeah. So here we're still doing pretty small regions. So we each like a numerical grid is represent a couple of nanometers. So the whole size is still like the micron scale.
Ah, okay. Yes.
So still a lot smaller than the experiment. But we, usually this can scale can scale up. Just if we use a much bigger grid size, then which means now you're not going to see the smaller domains, and of course the domain walls now will be really sharp. For example, people doing solidification, then they totally ignore what happened to the interface, so they do a lot bigger units. In principle, we can do this at different scales also at the interface.
Yes.
So in this case of simulations, we are talking about hundreds of nanometers, like a micron, on the order of micron for the system size.
Yeah. So I think also an indication already with this very first data which were published that it was a bit strange is that you see a lower loss tangent for the AC poled materials compared to the DC ones, and you would always somehow relate this loss to the domain wall density or so in part. So also I think this lower loss is also an indication that it's really getting this big units in a way.
You mean the light transparency, the loss? Or?
Yeah. So you showed also for the very initial experiments, they claimed that they have larger, that they have an increase in domain wall density, but in parallel they found a lower tangent delta. This doesn't really fit together.
Somehow mostly the existing publications, they all focused on the piezoelectricity.
Yes, okay.
And because all the crystal they saw are opaque, they because of the existence, see, most of the piezoelectric crystals, if you want to have very high piezoelectricity, usually you pull along the non-polar direction. So which means if at rhombohedral crystal, the polarization directions are along the body diagonals. So if you want to have high piezoelectricity, then usually you pull along one directions.
Yes.
Barium titanate is a tetragonal crystal. The polarization is along the cubic directions. So usually you pull along the 111 direction. But in this case, the rhombohedral crystal is actually different. If you can get a single domain along the 111 direction, and if you cut it, actually the piezoelectric anisotropy is actually the highest along the 111 direction. It just experimentally, it's difficult to say, hey, pull along 111, get a single domain, and then you cut it along that year, because now you have the problems of depolarization and things like that. So here in this case, you're using DC to pull along one direction, but now they still have this 109-degree domain walls form the layer structures, which also partially, now in this case, you can think of, they also get rid of some of the depolarization energy. So you can think of the single layer of crystals stacking together, separated by 109-degree domain walls. So actually two of the reviewers for our article say, hey, well, even I told Fei Li the same thing. I say, why don't you pull a single crystal to a single domain and then cut it? You say, well, experimentally, it's almost impossible to achieve.
Okay. Since you still have this kind of layered structure, so you have a single crystalline polarization in the plane, but not in the normal direction. Is there any possibility, for example, just do this kind of 10 times cycling polarization in one layer to have this single domain feature, and then return it by 90 degrees? Still keeping.
Oh no! This is actually still has out of plane polarization, because this is rhombohedral.
Ah, okay. Yes.
And the crystal is actually, the surface is all one, so you still have all three directions
Okay.
It's
Yeah.
along the diagonal.
Okay. Yeah. Okay.
And when you pole, so along the horizontal direction, there's a one plate, the polarization along maybe the in-plane components along one direction, you go to the next, you actually along the other two directions. So you change actually 109 degrees. But the Z direction, the polling direction, they all along the same direction. Now
Okay. Yes, I understand. Okay. Thanks a lot.
yeah, sure.
Anybody else have any questions?
Yes, if I may go next, I have a question. So you're using a linear increase and decrease in the polling, and I'm wondering if you investigated if other shapes of polling, more pulses, other types of polling voltages, if that makes a difference to the result or also to how long it takes to reach the end state.
Actually, there's there's not a lot of dependence. So you can, yeah, just using a square shape, and then you hold it, you reverse the direction, and you hold it. Or as in one of the slides show that you can try a different frequency. So which means even each period is long from like a 0.1 hertz to 100 hertz. So 3 orders of magnitude change in the frequency, you can achieve essentially the same without at the end. So it's pretty robust. It just need to go back and forth. Now, in terms of how many cycles, even after 5 cycles, they pretty much stabilize. That doesn't change much anymore. Yeah. Although some claims say you need to 10, 20 cycles.
Yeah, thank you very much for the very impressive talk.
Oh, thank you very much.
So I ask one more question, if I may. I'm from electrical engineering, not from material sciences. So it's a bit outside my field, but I'm wondering, can you then apply the strategy to other types of materials as well? Other classes of materials?
I think I could actually, even I thought about it. It's almost like you try to shake, a material. Mm-hmm. Just like when you try to screening, if I make an analogy, just like try to screen small particles from large particles. Typically if you manually try to screen, if you go back and forth, it's actually a lot more efficient than just tilt in one direction. So I think it is even this report, people not just single crystal, somehow even apply to ceramics. I've heard actually people also achieve better transparencies using AC. So it's to me not just the case of those polling of polarization. Maybe even apply a field to get the material response for other type of responses. If you're going back and forth, might actually a change now, whether change to the better or worse, but it will change the property. Of course, this is also similar to the issue of material fatigue. So like if you do many times, actually, well, getting worse in terms of fatigue. But in this case, it's only actually after a few times, we actually achieve not only better properties, but also in this case, the transparency. Yeah, but I can imagine that the same strategy might work for other type of problems, not even just polarization polling.
Thank you very much.
I think for magnetism, it would be also very interesting because in many cases, many domain walls, you have type of Barkhausen noise. So if you can get rid of the main walls, it's usually of advantage. So perhaps one can adapt these kind of strategies.
Maybe give it a try.
Yeah. Okay.
Okay, so is Sadie still in control?
Yes, I am.
Oh, okay.
No more questions. Does anybody else have any questions?
So perhaps one, do you see also, if you compare these DC and AC pole crystals, do you see a difference in hysteresis if you do the ferroelectric cycling?
Oh, let me see if I don't have the figure showing. Well, certainly there will be some change because the dielectric constant also.
Yes, I was wondering because the dielectric constant is enhanced by 35%, so it should be also.
Right. So
Well,
yeah, I don't have a figure showing how the loop changes, but I think there will be some changes. The dielectric constant you can derive.
Yeah, should be, yes.
Right.
Yeah. Okay.
Are there any more questions?
I have asked my questions. Thanks.
Yeah, Eka, sorry, missed the meeting in last month.
Yeah, so yeah, we were so short before having this done. So now I don't know what the DFG is planning. So probably they will have just a written evaluation. That's what I've heard. But I think they're still wondering what to do because no one knows when traveling will be possible again and so on. It's
right.
kind of a mess. Yeah, hopefully you all stay healthy.
Oh yeah, thank you. You too.
Yeah, so
Germany is doing pretty well, I guess.
I think our medical system is quite well prepared, but you never know. The number of deaths of casualties is now going up because if very old people catch this corona disease, then it's even with a good medical system quite difficult to save the life. Yes.
Yeah, but we had quite an early shutdown. We have already been, I think, in shutdown now for 3 weeks.
Yes.
4 weeks or something. Yeah, 4 weeks already nearly now, right?
Yeah.
The fourth
and
week.
I think now this doubling rate is so the number of infected people is down to 16 days or so until it doubles. So it's going down from this exponential case to a more handleable case. But the situation in New York City is really dramatic, isn't it?
Yeah. So I think a few people actually try to escape to our area. Also, we are much more remote area, but I can see quite a few New York places, you know.
The same was told to me from some people I know from Washington. So Manfred Wuttig also told me, you see so many New York number plates now in this area.
That's right.
Which is in a way bad because then they are bringing the disease all over the country. Yes.
Right. So, yeah.
But I think the other problem is Manhattan is so densely populated, you don't have a chance to separate the people. So it's not possible in a way.
That's true.
Yeah.
Okay. Well, great to see you guys, although remotely.
So thank you very much. Have a nice Easter weekend.
Oh, thank you. Yeah.
Yeah. So We have 2 national holidays, so tomorrow and on Monday we have national holidays, so our work will continue on Tuesday.
I see. So you get enough drinks? Can you still go out and get drinks?
Yeah, that we can.
Okay, that's good.
So,
Have a
okay.
good weekend.
Thank you very
Yeah, you
much.
too. Thank
Thanks
you.
for the invitation.
Yes.
Bye-bye.
Thank you.
Bye.
Bye-bye.
Healthy.